I've known James for, I think, 25 years or more, which is, longer than some of you have been around. And from the very beginning, he was one of the most enthusiastic physicists I knew, and one of the most clever outside the box guys I knew. And his career has since then, followed up on that. And he was also somebody who went to a Southern state school as an undergraduate, and I went to the University of North Carolina, and he went to Florida State, and we didn't read on basketball terms, but he then went to MIT, where I met him, and he did the highest precision mass measurements that have ever been done, comparing alkalis to carbon-12, and that was used in the chain that gives you the fine structure constant. So he has a precision background and a clever approach to things, and he took that to JILA, where he, after a stint with Lott and Woolitich, where he has done really fantastic work with cavities, and I think he's going to talk about it today, and I'm looking forward to it.
Great, thank you, Trey. So, I was a young pup grad student when Trey was a postdoc, and that's where we met. And I think it's just a case that forever I will think of, oh, Trey's my postdoc. Sort of that sort of relationship and sort of being in the trenches together was a lot of fun. I learned a ton from Trey in terms of mentorship. It's delightful. Thank you for the invitation to come tell you about the work we're doing in my lab at JILA in the University of Colorado. I'm going to tell you a collection of stories about what we're doing, where we're exploring collective effects in Cavity-QED. Okay. Let's see, that's not advancing. I just need to click on the screen. Is that it? Okay, let's see if I've got control now. I still don't have control. Be great if I could get control.
Oh, we put his on.
Okay, let me try now. Yeah, there we go. Now we're live. Okay. So what we're going to do in our system is we're going to work with laser cooled atoms. We're not having degenerate gases. Often when you think about cold atoms, you think about them bumping into each other. These days, you think about them being maybe in tweezers and having Rydberg interactions or something along those lines. But actually what we're going to do is we're going to create correlations and entanglement facilitated by an optical cavity. Okay. We have all these little individual atoms. These are graphics stolen from the Dave Weiland's Nobel Prize announcement, where in some sense, the atomic physics community has figured out how to get each of these little atoms to dance and jump around and do whatever we want. That's laser cooling and trapping and all this idea of getting rid of entropy of individual atoms, optical pumping, repair their quantum state, very low entropy states. But now we'd like them to not just be independent atoms, we'd like to have them join together to do something collective. Okay, we're going to explore that physics. The way we're going to create these little bonds, so now they're doing things together, not just as individual objects running in parallel, is we're going to use all the tools of quantum mechanics. So for instance, you may be very used to this idea of unitary dynamics. In fact, this is the more typical way that people think about doing quantum mechanics. I realize I'm Hamiltonian, and I let that Hamiltonian run, and something interesting happens. And that's why I'm calling unitary. But we're also very interested in the quantum measurement process, using the quantum measurement as a resource, as well as dissipation system. Okay. The broad themes.
Think about a slight microphone problem. Audio. Sorry.
Let's see, 1, 2, 3. That work? Sorry. It's not a problem.
Yeah, now we're loud and clear.
Excellent. Hello, everyone. Whoever's on Zoom.
And
Awesome. Okay. So hi, everyone on Zoom. Welcome to the talk. One of the themes of like what we like to explore, we're not a quantum computing group. That's not what we do, but we think about quantum sensing, quantum metrology, and connections to many body physics. Okay, those are sort of what we tend to work in. Here are 3 pictures of the optical cavities. We actually have 4 experiments running now. I'm not going to talk about the 4th one, although we're getting some nice preliminary results out of it. 2 in strontium. We use laser-cooled and trapped strontium atoms, and 1 laser-cooled and trapped rubidium atoms. I'm going to tell you today some stories about observing dynamical phases of BCS superconductors without having a superfluid. Okay, but we're going to tell you how we emulate that. I'm going to tell you about how we've realized cavity-mediated interactions in the context of building matter wave interferometers and some cool sort of interactions that we've engineered through the cavity and how we've realized the first entanglement enhanced matter wave interferometer. And if I have time, I will briefly mention this ring cavity experiment and some physics related to the idea of something called superradiance and building very, very stable frequency references. Okay, let's jump in. So the first topic is emulating dynamical phases of BCS superconductors. The experimental students, Dylan and Eric, led the charge here, but this is in close collaboration with the Anna Maria Ray's theory group at JILA. Okay, and Andrew Chu over here. Okay. I'm going to tell you stuff you know, probably know, you may not know. Whichever it is, sit back and relax. There's this idea that there's this phenomenon called superconductivity and superfluids. And one of the things that is interesting about this is that, you know, it spans from sort of nanokelvin to megakelvin. That this kind of physics can be seen at many different scales in many different contexts. So for instance, you can cool matter down and you can get into a superconducting state. So here's sort of this canonical picture of something floating here. I was at the Lorenz Center for a workshop for a while, and all these young undergrads were running down the hallway, and sitting in the corner was this thing. And that was Kamerlingh Onna's machine that he used to cool down to reach superfluidity and superconductivity. And so this is like big macroscopic objects. You just chill things down, okay? There was, you know, these breakthroughs where you can get degenerate Fermi gases in multiple groups around the world. And you can look at, for instance, BC to BCS crossover physics in these systems. And so this all seems pretty cold, you know, nanokelvin, Kelvin. But in fact, you know, for instance, people predict that you can have superfluids in neutron stars, okay? It's just the idea that when you have Fermi statistics involved, you can see all this kind of phenomena. Okay? So where does this come from? Here's a simple picture of it. This was put forward by Bardeen, Cooper, and Schrieffer a while ago, that you have some electrons moving through some lattice, and somehow they distort the lattice, and it's a little bit subtle that as a result of the screening that happens, you can actually get an attractive interaction between these electrons. So charges that like to repel each other suddenly start attracting each other. And this attractive interaction leads to a pairing mechanism. But one way to think about this attractive interaction is sort of as phonons, that you're distorting this lattice and you're launching sound waves in this lattice, and that can actually mediate interactions between these electrons. So you might draw it as something like this: 2 electrons in opposite spin states come in and they scatter by exchanging a phonon over here. So a very simple sort of Hamiltonian that describes this kind of sort of interaction looks like this. So you basically destroy electrons in momentum k prime and minus k prime in up and down, and you create a pair of electrons in momentum state k and minus k in up and down over here, and you have some interaction strength associated with the mediation through the lattice here, chi. Okay. So it's sort of a 4-body effective interaction mediated by this phonon over here. And what I'm really going to tell you about today is how we basically replace this phonon with photons. It's not exactly correct what I'm telling you, but it's not a bad approximation, okay, in order to explore this physics. So here's a model picture of this BCS Hamiltonian. And one of the things you're always competing against is the single particle physics, which is that you have single particle dispersion, i.e. kinetic energy in the system. And so you can describe that as, you know, sort of here's the energy, kinetic energy associated with a particle and momentum k and spin state sigma over here. And we all know about sort of the Fermi distribution over here, right? So if you're below this Fermi level, then basically the chance of finding the electron there is 1. And above it at 0 temperature, okay, there's no probability. So we think of this as sort of unoccupied states that we'll think of as holes. So occupied, not occupied over here. Now, what the BCS theory says is, well, let's actually add this sort of interaction and let's make it negative. So if this interaction is there, actually the system can somehow lower its total energy as a result of this interaction in the system. What that means is you need sort of the energy scales associated with this term to be comparable to the energy scales associated with this term. And it turns out where that's going to matter is near the Fermi surface over here. That's where you're going to see a perturbation to the system. It's right near this edge. So you might say, well, what kind of wave functions can I write down that would actually minimize the energy of this Hamiltonian for states near the Fermi edge, Fermi surface? So if you do that, you might imagine, well, I'll just try to write a product state of different momentum states where maybe minus k is occupied, but k is not occupied. But if you actually just do, just calculate the matrix element of this state across here, you find actually that doesn't work. That doesn't give you any change in energy. So you throw that one away. Okay, that one doesn't work. So you come along, you start fiddling around, you ask what kind of state actually would minimize or reduce the energy. And you find out it's states where you say, for a given momentum state k, I both have it occupied in minus k and plus k and not occupied. You go into a coherent superposition state of these two possibilities right here. Okay. And it turns out when you look at this Hamiltonian, you just calculate sort of hit it from the right, with a ket, and from the left with a bra, you find out that actually this has a reduction in the energy from that term. So it turns out this becomes the ground state of the system. Okay. What does that have to do with our system? Well, it turns out that very early on, Phil Anderson said, well, look, maybe we can make a mapping in this system between saying that I have k and minus k occupied by electrons. We'll call that spin up. And if I don't have any electrons in that state, I'll call that spin down. And I'll label the spin up, spin down here with some momentum label k over here. So now you take this Hamiltonian, I put the interaction term first now, and you actually map this onto some spin operators. So this is, for instance, a raising operator in state k and a lowering operator in state k prime over here. And then the kinetic energy you think of as an SZ operator over here. This allows you to map this four-body interaction to essentially an interacting spin model. Okay. So if you ask this idea of superpositions, what does it mean when I have a spin system? I say I'm in a superposition of occupied and not occupied. Well, that actually corresponds to, for instance, being in a superposition. So that would be a block vector that's sort of pointing horizontally. Specifically on the block sphere, here's a north pole describing these spin operators over here. And for some momentum state k, let's say way below the Fermi edge, actually it's very more likely to be occupied. But as I come towards the Fermi edge, actually it becomes more likely to be in a superposition of occupied and not occupied. Okay. And if I go way above the Fermi edge, actually it's more likely to be not occupied. And this becomes the ground state. And it turns out if you add all these individual block vectors together, the individual k states, you get some macroscopic collective block vector here, where I'm going to, you see, it doesn't have a k label on it. So this means collective. It's the sum of all those. Turns out that the BCS energy gap, or order parameter over here, is just this interaction strength times S minus. And that's the energy. Okay. This is really the energy that it takes to break one superposition state in the system. Okay, to move away from that ground state.
So how should I understand the idea of a pair breaking, which is the way we often think of how robust the
So let me give you,
in terms of this block.
Let me give you I will come back and give you an example very briefly where we introduce a term that's a little bit like a pair breaking term, not quite, but it has some analogies. We're still trying to figure out in our system how to truly introduce in a controllable way a pair breaking term. One of the things that we think, let me just pause and sort of give a broad overview. Okay. one of the goals here is to say, in what way can we make connections to this kind of many body phenomena? And then having done that, introduce complexity in a controlled way. So to start with, we're overjoyed that this system does not have pair breaking terms. And then we'd like to say, now can we start adding them and look at what happens and how does the system break down as we add those terms? Does that make sense? One way we're going to do that is we're going to actually couple our two-level systems in this to a third level. And it's actually going to have nice analogies to, for instance, the RF spectroscopy that was done by Debbie, proposed by Peter Zoller et al., and Debbie Jen and Wolfgang and Rudy Graham and others in that day.
Okay, so far, this looks pretty single particle, although underneath you have the electron phonon interaction.
It's this interaction. That's the collective.
But the block vector picture
Sure.
doesn't look like it's got interactions in it, but there's a.
It's the fact that this is the ground state.
Yeah.
Like block vectors are just describing the state.
Right.
Right. So that's just sort of,
State.
but it's single particle state. But why would they choose this to be their ground state? It's because of that collective interaction. Okay. So we're going to have interacting spins. Mm-hmm. Mm-hmm. Sorry.
Gap equation, the gap is proportional to the couplers.
The gap is proportional to this chi over here in the transverse component of this collective block vector. Mm-hmm.
Different than PCS here, because in PCS, I think the gap was exponentially more than the couplers.
So we have a finite system. So I want to be a little bit careful about talking about some thermodynamic limit in this system. Okay. Mm-hmm. We don't have a degenerate gas. What we're doing this in is we have a laser cooling and trapping experiment that Dylan and Eric have made work, where we laser cool and trap atoms inside of a high finesse cavity over here. The length is about 5 centimeters and it has a finesse of about 30,000. Light bounces back and forth about 30,000 times before it escapes. The cavity line width is about 150 kilohertz. The mode waste is about 70 microns. We trap the atoms tightly on axis in an intracavity magic wavelength lattice so that the excited state and ground state get the same potential energy shift while still being trapped. It's a standard trick of, for instance, optical lattice clocks. Okay. We do that so that along the cavity axis, the atoms are in the Lamb-Dickey regime, i.e. they're tightly confined, so we can ignore Doppler broadening in the system. So even though we're at finite temperature, we're not cooling to the ground state, we can ignore any kind of Doppler broadening. And again, we're tightly on axis over here. For people who know about this, our single particle cooperativity is about 0.4. What actually matters for these experiments is the collective cooperativity. This is usually what we always care about, and that's about 10 to the 5. We want that number to be much bigger than 1. Basically, it's telling you sort of something about the ratio of the degree to which the atoms collectively interact with the cavity mode versus scattering photons into free space. Free space is bad. We don't want that. We want this interaction with the cavity, and this tells you that it's very strong. Okay, so where do we get our interactions from? Well, it turns out that we showed a while back that, for instance, if you put in one atom at, say, lattice site K prime and another atom at lattice site K, one is in the excited state, one is in the ground state in strontium, then, in fact, this is the clock transition. This is a 1.35 millihertz radiative line width transition. You can actually get a process where if you detune the cavity off resonance from this transition by about 50 megahertz, you can get a process where an atom decays and emits a photon into the cavity, and before it has a chance to escape, it gets absorbed. And notice that they flip their states in this process by exchanging that photon. So what it looks like is, if we call this spin up and that spin down, it looks like I started with up down, I exchanged a photon, and now I have down up. So it looks like an exchange interaction, but it's all to all, because all the atoms are interacting with the cavity over here. So in fact, we can rewrite this in terms of a collective raising and lowering operators S plus and S minus over here. But underneath, inside of it, if you look at what's the sum is summing over inside these collective operators, it's these kind of pairwise interactions, but it's all to all in the system. Okay. So what we're going to do is essentially we're going to say we're going to take these momentum labels K and K prime, and we're going to replace them with lattice site labels K and K prime in our system. And that's going to complete the mapping of that BCS Hamiltonian onto our system. Okay. You might ask, well, this is pretty weak. It's actually pretty big. The characteristic collective energy scale of this interaction can be as large as 1.5 megahertz in the system. Okay, so compared to most cold atom experiments where you might imagine sort of kilohertz, few kilohertz, this is actually quite a large scale over here. Okay.
James, on the previous slide, what does lifetime 118 seconds or 22 microseconds mean?
There are two different transitions we'll work with. The original work where we saw the spin exchange Hamiltonian and saw its presence was actually done on the clock transition, the one that's shown here. We actually figured out a Cavity-QED technique. So that star there is to remind me to tell you that we actually measured that using our cavity in a very clever, in my mind, dispersive trick that we could use to measure that lifetime. But we can also do physics on the triplet P1 transition here, and it has a lifetime of about 22 microseconds. In fact, most of the physics I'm going to tell you about today is on this 22 microsecond lifetime transition, the triplet P1. Okay. Mm-hmm.
So this BCS Hamiltonian you showed, so it also is known as Richardson Hamiltonian nuclear physics.
Yeah.
So in fact, it's not essentially that.
Yeah, it's like the Richardson-Godine model, exactly. Yeah, that's right. So
Actually, what you're doing is closer to the ladder.
yeah, I think so. I think there are other connections to other systems. It's a very generic sort of Hamiltonian and interaction system. And what we're going to do is, again, we're going to start with something that we think we understand. And once we understand it, it allows us to add complexity in the future and go beyond it. That's where we're pushing in the future. Mm-hmm.
Yeah, but this nuclear Hamiltonian is more there's more detailed solution than just nuclear BCS that you showed. Right?
Sure.
Exact solution.
No, it has an exact solution. Yeah. There's a nice review paper by, I'm sorry, I can't remember who the other authors are, but Anna Maria has a very nice review paper on exactly this physics.
I missed what the 50 megahertz was.
Yeah. So the atomic transition frequency, this vertically is frequency. So here's the ground state, here's the optically excited state of the atom. But we can change the cavity length here to tune the resonant mode of the cavity so that it's not resonant with this atomic transition. We move it off by about 50 megahertz. And in that limit, that's a limit where we operate such that it's much more likely if a photon gets dumped into the cavity that it gets absorbed by another atom before it escapes from the cavity. So by working at a detuned limit, we can actually get this unitary or Hamiltonian-like interaction while suppressing collective decay called superradiance, because that falls off like 1 over detuning squared.
Now that seems like a piece of cake when your lifetime is 118 seconds, but when your lifetime is 22 microseconds, it doesn't sound like it's so.
50 megahertz? Yeah, no, it's plenty. You can do adiabatic elimination and you sort of get, many cycles of sort of coherent interaction in the system.
Okay.
Mm-hmm. So in the past, I'll just point out that we've applied this to look at dynamical phase transitions of the style called the LMG model, this Lipkin-Meshkov-Glick model, where essentially you have this kind of interaction term plus a transverse field plus an axial field. And you can sort of look at sort of transitions and the dynamics of the system as you vary these parameters. And you can see something that looks like a ferromagnetic sort of self-trapping phase. If you're thinking about tunneling physics, there's a nice analogy there in cold atoms, or a paramagnetic phase where essentially the system begins to oscillate rapidly. And so we've explored that previously. That's not what I'm going to tell you about today. What I want to tell you about is that Levetov and Guari and others had predicted that there should be dynamical phases of a BCS superconductor if you perform a quench on the superconductor. And so, you have sort of your interaction term plus dispersion in homogeneity. It's what we call it in atomic physics. And the idea is somehow you change some parameters in the Hamiltonian very rapidly, and you actually look at how this BCS energy scale, this sort of gap, behaves as a function of time. And in some regions, you start with a large gap, but then it actually quickly decays. In other cases, you introduce wiggles that are sometimes referred to as Higgs oscillations, but then it sort of comes to steady state. And in other cases, you see persistent oscillations, and sometimes this is called a phase 3, was the prediction. Turns out this is really hard to see. Why? Because when you go and quench a real superconductor, actually all those other bad terms that have been alluded to kick in. There are other things that that quench does to your superconductor, and it screws it up. On the other hand, we have a relatively clean system where we can apply quenches, and because we don't have all that other physics built in, we can try and look for this physics. Okay, so the key is that we have this interaction term over here. We need to be able to put in some programmable dispersion, which we simply do by creating inhomogeneous AC Stark shifts on that transition. So that allows us to program in sort of these shifts that are vary with lattice height in our system. Okay, so we can program in, for instance, dispersion relationships that look like this, where now this is sort of K Fermi, harkening back to this idea of momentum state. But in reality, we're talking about lattice height in the cavity at this point in the real experiment. Okay. Now, it turns out in degenerate gases, the idea of how do you actually measure this BCS energy gap was quite hard. What's actually nice in our system is that, in fact, we are only 50 megahertz detuned, and there's a little bit of light that does leak out of the cavity. In fact, there's some field that leaks out of the cavity, and we can detect that on a photodetector or using heterodyne detection. And it turns out that that field that we can detect leaking out tells us directly what S minus is. Okay, so by just detecting a little bit of light that leaks out from our system, we can actually directly track in time what this order parameter is doing. Okay, and not only measure its magnitude, but in principle also its complex nature. Okay, and look at that. So it turns out this is a very, very easily accessible sort of order parameter in our system, which was hard to actually access in other experiments with cold gases. So here's the idea that there's going to be some kind of phase diagram with respect to sort of the dynamical behavior of this object after a quench. The quenches, we're going to go from very large interaction strength compared to the inhomogeneity. EW is the inhomogeneity. Very large interaction strength, small inhomogeneity. We're going to start in a state that's out here. And we're essentially going to quench it to a point on this diagram here. And we're going to ask, does the coherence persist? Does it decay? Or does it oscillate over here? And so we're going to start way out here, and we're going to quench to different points on this diagram. So here's an example of data. So we're actually looking at the field leaking out of the cavity. That tells us the equivalent of this BCS order parameter. And if we start at very low atom number over here, then the product chi times n that sets the energy scale is of order 0.2 megahertz. Okay. And as a result, we first prepare a state that's very close to the ground state of the infinitely interacting system where chi basically goes to infinity. And then we're applying this quench. And so what it does is when we actually sort of turn on our inhomogeneity over here, so we start with the inhomogeneities off, and then we turn them on right at t equals 0, we see a rapid collapse in the order parameter. This would be equivalent to the phase 1. So we've quenched into the phase 1 region over here. This is just single particle inhomogeneity. This is single particle physics, this part, right?
So would it be reasonable to think that the chi in this case is collapsing because of the fact that you don't essentially have n atoms anymore because of the inhomogeneity?
Yeah, it is. This is for atomic physicists. This is like trivial. This is like, I did a pi over 2 pulse and I have inhomogeneity and my block vectors just begin to freely precess. And therefore the average block vector goes to 0. This is the trivial phase over here. This is the single particle inhomogeneous broadened phase.
Okay.
Mm-hmm. Let me first give the mean field stuff, and then we'll come back to that kind of question in just a second, because I think you're asking good questions. We don't know, but right now we're looking at mean field, right? At the moment, things are not high Q, in part because when we do our first rotations, it turns out we're actually coupling to some motional states, some sideband transitions in the traps. And we think that's introducing some extra inhomogeneity that causes a little bit of collapse at long time that we don't fully understand. Like I'm telling you our guess. So there are some things we don't quite understand about our data.
So the picture you gave us of the block vector makes you think, oh, then there's going to be an echo.
If we wanted to, we could apply an echo and we could try and look for a revival. We're not going to do that. instead we're going to focus on what happens if we modify and allow the interaction strength mediated by the cavity to become larger. So that's what we do as we go up in color here. As we go up in color, what we're doing is we're changing the characteristic interaction strength by increasing the atom number that we load into the cavity. Chi-n is what sets the scale for the interaction strength. By having more atoms, make it more collective, you get more interactions. And so as a result, we can go to 0.5, 0.7, and up to 1.2 megahertz for this data. And suddenly you see that the coherence lasts for a very long time. And that's actually a result of the interaction via the cavity that's stabilizing that coherence in the system.
It's like in ECDL where you have an external cavity and it's feeding back onto the regimes of coupling where you may have forwards collapse versus oscillations. Can this be thought of?
Sorry, what was the mechanical system or the physical system?
A median coupling thing outside, and depending on the coupling between the cavity, they can have forwards collapse or oscillations.
It's possible, but this is the physics we're looking at is in a unitary limit. Whereas if you tell me ECDL, I immediately think dissipation has got to be critical to that system. So if we look at this data over here, we can actually look at the lifetime, some characteristic measure of the lifetime of how long the coherence lives for as a function of n and chi-n as a result. And we see this transition where you go from collapse to the coherence being preserved. We can also look at sort of like the average coherence left over after some amount of time and also see we have this transition over here.
Is the fact that it saturates at 30
Yeah.
somehow related to the 22?
Yeah. So this is in some sense, the radiative decay line width is related to that time scale, 22 microseconds is related to the probability of the excited state decaying. This isn't an amplitude. So in fact, the radiative lifetime would limit this to 2 times 22, which would be 44. And then it turns out that we know that we have some other background single particle inhomogeneity, which doesn't have the right spectral properties to be gap protected. In other words, gap protection only works if you have some static low frequency sort of noise in your system. Then you can gap protect against. But if you have rapidly oscillating or equivalently homogeneous broadening in your system that has some characteristic, sort of frequency scale that in a power spectrum would be infinite, you can't gap protect against that. Okay, and so that kind of thing we can't fix, and so that's the combination of those two is limiting it. I would say over 50% of it is just spontaneous emission.
Oh yeah, what is delta S on the y-axis of the phase diagram?
Yeah, we haven't gone there. So right now we are going to jump to here. We also are going to modify and create an energy gap in our dispersion relationship compared to the width of the sort of spread of the dispersion. I'll show you on the next slide over here. But right now you can ignore it. We're basically exploring along this line where essentially we just have some sort of broadening of our sort of transition frequencies. And we're comparing that to the interaction strength over here.
All the parameters, the gap.
Yes.
Experimentally.
It is actually the complex field detected in heterodyne detection. And then you can rescale to put that in terms of a gap energy.
Because the gap was at the Fermi level.
There's no real Fermi level here.
No, but you
Yeah.
translated into
Yeah.
space.
Yes, that's true.
So then how are you picking up the specific case that correspond to the...
We aren't. We're basically saying all of the interesting physics happens near the Fermi edge, and then we're basically ignoring that, they're not these states that are way far away.
It would be what, in a space? You had a mapping from the Fermi.
We did. I mean, if you, basically we're saying, let's pretend as though there are atoms that sort of go out to lattice sites all the way out to the mirrors and beyond. But in reality, we can just truncate our system and just have a finite range of lattice sites, right? So I think at that point we give up the analogy to the Fermi edge. But what we can say is, if you take the average transition frequency, you might want to think of that as the Fermi edge. Does that help? So I broaden, but you can ask, what's the average atomic transition frequency? You can think of that as, well, that's sort of the energy at the Fermi surface of the system.
Because your frequency selecting emitted light, let's say, what K you're selecting.
It's not, it's really that at t equals 0, think of it as all the atoms actually have identical transition frequencies. That just, it's like having an infinite mass particle. There is no change in kinetic energy. We're imposing it and creating a spread by applying these inhomogeneous light shifts across our ensemble. So now we're spreading around that 0, that delta function. And then now we're asking what happens then. So it's kind of like, sort of saying, well, how rapid around the Fermi surface is the sort of change in kinetic energy? If that sort of analogy you can hang your hat on.
So you're saying that your imposed inhomogeneity is the effective temperature.
Yes.
And if there was no inhomogeneity, the temperature would be 0.
Not quite, right? Because the kinetic energy term exists independent of temperature, right? This is really just saying as a function of K, in this case, lattice site, what is the effective transition frequency between spin up and spin down? So it turns out that if you look at this data, and if we tune into different regimes, you'll notice in the data after this quench, occasionally you'll see these little bumps. We can actually enhance those bumps by tuning our systems in different regimes. We have another experiment I'm going to briefly touch on where actually these bumps are even more dramatic in sort of the equivalent of this BCS gap parameter. It turns out that people have been looking for those, and only recently did Christian Vale's group actually see this in a degenerate Fermi gas. And they could actually see these Higgs oscillations, and we're kind of seeing analogies to those after the quench as well. So these oscillations in the amplitude. For the phase 3, in order to see these persistent oscillations, what we do is we actually create a funny dispersion relationship with a gap. So in fact, sort of some atoms have this transition frequency and some atoms have this transition frequency plus some inhomogeneity. And there, as we increase the degree of that sort of gap over here, that's moving vertically in this phase diagram is what we're doing. When we do that, we see that actually we can open up these oscillations that are over here, and these are analogies to the phase 3. Yeah.
So they were quenching.
Yes. Yeah.
In your case, you're not doing that.
That's right. So in those papers, they were actually quenching chi is what we're doing. And what we're doing here is not quite that. And it has to do with sort of that we're actually preparing in the infinitely interacting state here. And then in their system, what they were doing is they were starting with on the sort of this mappings, Anderson mapping, you would say actually you start with the atoms initialized with the spread of block vectors, right? In their polar angle, right? Exactly. And then essentially you quench on chi and then you induce the oscillations from this. That is not that, just to be fair. Yep. Yeah, we do. Basically, it's a kick to the system that's arising from changing that competition between the two. But you're absolutely right. It's not exactly the same experiment.
Yes. Sorry. But so there's all this phase, dynamical phases, they correspond to non-equilibrium states that never thermalize.
Yeah, we definitely thermalize because it's a real experiment. Bad stuff happens. In this case, it's not coherent quantum dynamics. It's that we have inhomogeneities and imperfections in a real experiment that make it go away. Mm-hmm. I'm not going to go into it because I have some other things I want to tell you about today, but essentially we can model this and we can understand what kind of orbits give rise to these oscillations over here, and they behave the way we expect when we model them, okay? I also want to briefly touch on that in the system, because we can look at the light leaking out, and this gives us sort of a measure of the order parameter over here. I want to harken back to these measurements where people did RF spectroscopy in degenerate gases in order to get some handle on what the order parameter was in that system. But it actually, it's a little bit confusing. Essentially, what they were doing is they were creating a degenerate gas with, say, 2 spin states, and they would sort of have these states interacting and then try and use RF to couple to a non-interacting state over here. It turns out, again, I'm not going to tell you, the details. There's a paper on the archive on it, but I just want to say that essentially we can create a system where a ground state and an excited state interact via the cavity. But this third atomic state, if we transfer amplitude into that state, it does not interact. And we can actually provide a coupling whose strength we can control that couples this excited state to this state over here, which acts like this coupling over here. And we can actually measure the equivalent of this RF spectroscopy, these shifts. And what you see is that actually it's very clear in our data that you have two different energy scales. One is this BCS gap that scales like chi-n, but there's a separate one, which in the literature was referred to as a spectral gap. So we'll adopt that sort of naming convention that says actually your ability to sort of create a collective gap that protects you against transfer of amplitude to this non-interacting state, that actually depends on the number of atoms in the ground state. So what we're seeing is sort of the size of this gap that we measure as a function of the number of atoms in the ground state. And as the number of atoms in the ground state is reduced, we see that actually this energy gap goes down. So we can actually resolve and tell the difference between those two in the system. Okay, so again, I want to say that we've made this analogy and we're saying, look, we can make these connections. And the goal going forward is thinking about how do we add complexity? For instance, is it possible to look at P plus IP models? Can we go to higher partial wave superconductors and start modeling those? Can we understand how to introduce pair breaking terms and see like how far can you push this analogy and see if there are regimes where we can really get understanding from these systems? So with that, I'm going to switch and tell you about cavity-mediated interactions in matter wave interferometry. Great. This is going to be a little bit quick, given our time. But the basic idea is that if I build a quantum sensor, I want to read out my quantum sensor, but there's some fundamental quantum fuzziness in my ability to do that. And it turns out if you can create entanglement between the atoms, you can create states such as squeeze states that actually allow you to, for instance, tell time or acceleration more precisely. Okay, but the goal is you need to get these atoms entangled with each other so they can cooperate with each other to modify each other's quantum noise. Here's a plot of spectroscopic enhancements over the standard quantum limit as a function of year, ion traps, cold gases, whatnot. Our group has created these kinds of entangled states. They're the red points over here. So we've seen Heisenberg scaling, not Heisenberg limit, but Heisenberg scaling in this work. And the record at the moment is around 18 dB, both in rubidium, both using what are called quantum non-demolition measurements, okay, with rubidium atoms in a cavity. It's our group and Mark Kasovich's group at Stanford. Recently, I'm not going to tell you about this point, but it's a new point on this plot. Where in a collaboration with Juni's group, we were able to actually squeeze two different ensembles of strontium and build a differential clock measurements that was enhanced via the squeezing. Okay, so people have applied this. One of the things that was missing was, has anyone applied this in the context of matter wave interferometers? And so we actually set out to do that. If you are a student and you don't know what matter wave interferometers are, they're sort of the sort of using matter waves instead of optical waves and using light pulses to sort of cause them to traverse along different paths and then get an interference signal. So it's replacing, sort of optical waves with the de Broglie wave. Okay, turns out very, very good for precision measurement. You can do things very, very precisely by doing that. So in 2022, we were able to build the first entanglement enhanced matter wave interferometer. Qingyi and Graham deserve a lot of credit for this. This is not a non-trivial experiment where we actually start with we picture this on block spheres, but sometimes there are these sort of space-time diagrams that we use for matter wave interferometers. But we can think of it as, sort of in a superposition of two different momentum states separated by two photon recoils over here. And then we actually do some operation that creates an entangled state, and then we inject that into a matter wave interferometer and ask, do we have improved sensitivity at the output? And the take-home message is, yeah, it works. Okay, we were able to achieve that for the first time. And just recently, this year, now there's a second group that has done this and been able to demonstrate an enhancement, basically at the same level that we were able to, but using collisions between atoms to create the entanglement rather than light matter. In that system, we trap atoms tightly along a cavity axis over here in rubidium, and we let them fall, accelerated by gravity, but guided by repulsive dipole trap we build up inside the cavity. We can do all the kind of operations you would like to do in order to manipulate the momentum states. We can actually, we're going to send all of our tones in along the cavity axis over here. So for instance, we can flip both the momentum state and the spin state, ground hyperfine states. And we can put atoms in superpositions of two different momentum states and see that in some spectroscopy over here. We can do Bragg, large momentum transfer, by injecting tones into the cavity and sort of build up separation of momentum space over here. Doing this in a high finesse cavity had never been done before, so that was already sort of a lot of work just to get that running at a high quality. So you put all this together, those pieces, and now you can build beam splitters over here and build an interferometer. We can see interference fringes. And in fact, if you look at the phase that it accrues in the interferometer, it goes like t squared. It's the same kind of, sort of like the phase is like position. It's like if I drop a rock, its position changes like t squared, right? And so we're actually sensitive to accelerations over here. Yeah. That's all single particle physics so far, everything I've told you. The way we actually introduce interactions in this case is by taking advantage of the fact that the two ground states, the two momentum states over here, we also flip the internal hyperfine state of those two. And these states are separated by about 6.8 gigahertz. And so we tune a cavity mode, maybe about 500 megahertz off resonance from this up to E transition. And so if no atoms are in the cavity resonance frequency is here, you put some atoms in this state, and that cavity mode shifts in frequency. It's like every atom in up acts like a little piece of glass that has some index of refraction that shifts the cavity mode by an amount proportional to the number of atoms in up. This can be described by what's called a QED Hamiltonian, where you're just saying, look, C dagger C are operators describing the cavity mode, and somehow the frequency of this mode depends on the number of atoms in up. Okay. How does this compare to fluorescence detection? People detect and count atoms all the time. The key point is, by actually looking at the light that leaks out of the cavity, I can measure the cavity frequency shift, but I can't tell you which atom is in spin up. I gain no single particle information. So it's a collective measurement that allows atoms to not collapse, but remain in a superposition of spin up and spin down while still counting the number of atoms in each state. That's what makes it different from what you're used to. It makes it very special and allows you to create entangled states. Here's an example. We actually look at homodine detection of the reflected field from the cavity. And so, for instance, you get these dispersive shifts depending on the number of atoms. If you can do that very precisely, you can effectively form a Hamiltonian that allows you to measure the spin projection JZ of your ensemble. And so in some sense, you start out with some very large uncertainty, but on a given trial, you actually reduce the uncertainty in the angular orientation of the block vector below the original unentangled level. And by doing that, you can actually show that you get angular sensitivity that drops below the standard quantum limit, 1/√n radians over here. There's another approach. Yeah, so we see about 3.4 dB. This is directly observed. We're not background subtracting. There's no spam correction, anything like that. This is what we see. There's another approach where you take the same dispersive shift, but you actually apply a tone off resonance from the cavity. Depending on the spin projection JZ, this cavity resonance changes. So you can set up a system where the number of atoms that get in, or number of photons that get in the cavity now depends on JZ, on the spin projection on that trial. So what that means is we can replace, at least in some approximation, C dagger C with JZ. And now I've got a Hamiltonian that looks like one-axis twisting Hamiltonian. It's a JZ squared Hamiltonian. I use the word one-axis twisting. Why is it called that? If this is my original thermal sort of quantum uncertainty in the orientation of my block vector, what this does is it shears the quantum noise. If I'm above the equator, I precess one way. If I'm below the equator, I precess the other way. So I get a shearing, and it actually reduces the uncertainty in this quantum state along that direction. We can then apply rotations to put that wherever we want to get enhanced sensitivity. Okay. So we do that. We see we can produce about 2.5 dB of squeezing below the standard quantum limit. And then we inject it to an interferometer. We run the whole darn thing, and we see an improvement at the output. And that's the first time anyone's ever done that. Okay. You might ask, here's QED, here's unitary dynamics, which one wins? I'll just say that we've thought about this, and it really depends on how good you can build the quantum efficiency of your QED measurement. But if you can actually make it very high, bigger than 3/16, it's not that high of a bar. We've done that. Then it appears that you win by using QED measurements. In terms of given a set of resources, that's what you should do. Okay. I'm just going to give a highlight that we've also engineered cavity-mediated momentum exchange interactions where we don't have hyperfine labels on our momentum states. In fact, we can have a system where imagine two atoms that are moving at two different momenta inside the cavity. You say one, the average momentum is P naught moving downwards, but one is moving a little slower and one a little faster over here. Then we can apply dressing laser tones to the cavity and we can engineer a system where essentially this atom absorbs, emits a photon to the cavity. The other one absorbs it and flips. Oh, this is exactly like the exchange interaction. This is a two-level system. Here's the exchange Hamiltonian over here. So in fact, we can build the equivalent of a spin exchange Hamiltonian, but for momentum states. Okay. And so there's a nice sort of physical picture that when you build this superposition of momentum states, you build sort of a density gradient in the system. And essentially what's happening is when you send in your dressing laser, you actually get blue shifted, red shifted, Doppler shifted photons scattered off of that. And it turns out that when you do that, you can actually build an effective two photon coupling that couples the momentum states between these sidebands. Are we generating it? Well, we can rewrite J plus J minus as total J squared minus JZ squared over here. And so we can look for, is there a Z dependent change in the precession rate of our block vector? And so we can actually see that over here and we can change the sign of the interaction chi and see it flip sign as well. This, we think in the future, we can harness to create entanglement. The other term is interesting. It's the total J squared term over here. What's that one? Well, we have data on it. I'm going to tell you, I'm going to show you the cartoon. Normally a matter wave interferometer, I hit my system with a pi/2 pulse here, and the part of the cloud that absorbed the photon recoils, and the part that didn't doesn't do anything. It just keeps moving along. And they separate as a function of time. And this shows up as a drop in the coherence that you see as a function of delay time after that pi/2. Turns out that when we have this interaction on, what happens is the coherence persists for a lot longer than you would have expected. And what this means is it's almost as though the wave packets are no longer separating due to this interaction. And so one question is, are they connected by a spring or is it like they're frozen in place? And so we can actually take data on that by actually allowing them to separate for a little bit, but then turning on the interaction. In fact, they ring. We get a ringing in the contrast as though the two parts of the wave packet are bouncing with respect to each other. And in fact, this numerical, let me see if I can do it again, simulation over here with the interactions off, here are the two wave packets separating. But when we have the interaction on, they stay combined. They're really, it's like they're connected with the spring. And the spring's characteristic resonance frequency is chi n. It's this sort of collective interaction.
So the two wave packets are physically not separated.
Yeah. So let's do this Gedanken experiment. Because like, here's a Gedanken experiment that really hammers home like how freaking weird is what I'm telling you right now, okay? Imagine I had a single photon source. I had N atoms that are ready to absorb that photon. And I send that single photon in. We all know what happens. If I have no interactions, one of those atoms absorbs. It comes shooting out of the cloud sometime later at a velocity h bar k over m. That's just conservation of momentum. Now let's imagine I turn on these momentum exchange interactions in my cavity. I shoot that single photon, and what I'm telling you is the whole cloud recoils. And it recoils at a velocity h bar k divided by nm. It's a collective recoil mechanism. So this actually has really nice analogies to, for instance, that you can suppress Doppler dephasing or wave packet separation, similar to Mössbauer or Lamb-Dickey spectroscopy over here. These are really important techniques. This is, sort of Mössbauer allowed us to, for instance, be able to see the gravitational redshift for the first time, right? By trapping, radioactive nuclei in crystals, you can sort of have a collective recoil. Or for instance, all of the, optical clocks are based on sort of this tight trapping of Lamb-Dickey. And so this is kind of a weird thing that now in sort of matter wave interferometers, we have something similar to that. But you might say, well, that's a cool matter wave interferometer thing, but come on, like it's some weird thing to do with matter wave interferometers. So you might ask, can we see that same effect where we suppress sort of this recoil, but on optical transition? And so in one of our strontium systems, if we have a ring cavity, and so we put a cloud in there and we actually drive and put atoms in a superposition of the upper state and the lower state. And normally this would dephase on some Doppler dephasing timescale shown here. But in fact, what we see is if we trap the atoms in intracavity Lamb-Dickey regime, here's the coherence as a function of time, that's the blue. But if we don't trap them and we have these interactions on, actually we see the coherence lasts a lot longer. So in fact, we can protect optical coherence using this exchange interaction mediated by the cavity as well. I gotta stop soon, but I want to tell you, I'm going to give you a highlight, right? It's 11:57, so I'm going to stop any moment now. There's this thing called two-axis counter twisting. There was this original paper that kicked off this whole idea of squeezing. One-axis twisting, that's the JZ square, but there's this other thing called two-axis counter twisting over here. No one has known how to do that. And so we actually figured out how to do that. That's been 30 years. And it turns out that if we simply apply two dressing tones and we tune things up right, we can have the original momentum exchange interaction I was telling you about, where they flip their states. But what we can do is we can turn on an additional 4-photon process where I emit a photon and then it actually eventually gets absorbed over here. And this corresponds to pairs of atoms actually flipping their state together. And by tuning the relative strengths of those two pumps, we can sort of combine these two Hamiltonians to get whatever we want. This gives us almost an arbitrary XYZ Hamiltonian, all-to-all engineering in the system. And that means we can engineer, for instance, JX squared Hamiltonians. We can also engineer this two-axis counter twisting. And we've actually seen this. So this is data showing the flow lines of block vectors prepared at various points on the block sphere. And you see the bifurcation point. There's another one on the opposite side, and there are 3 stable points on this. So this is really true two-axis counter twisting. We can zoom in on the bifurcation point. We can see that there's exponential growth. But we can go further. Okay, so we have 2 body interaction terms. That's like J plus squared or J plus J minus. But we can also go to 3 body interactions. And so what you should think about this is it's like having 3 atoms in spin up. This is actually a momentum state at this point. And they all flip their spins to down over here. And we actually do this by sort of applying the right laser frequencies, and we can drive between this initial state and this final state. It's actually a 3-atom, 6-photon process. That's what we're driving in this system. And so we can actually simply tune this process onto resonance by choosing the right frequency difference between these 2 applied dressing lasers. And we actually have data that shows that that 3-body term is there, and it's in the system. We can also sort of look at sort of the dynamics looking down from the North Pole. Let me skip that. I will say there's a signature even of a 4-body term that we can actually go and actually see that we have a process where 4 atoms flip their state in concert with each other. And that's actually a 4-atom, 8-photon process over here. Okay, with that, I'm going to skip over. We also do this stuff with superradiants, trying to make very, very stable lasers. That's a work in progress. We think we could get down into the few to the minus 18 at 1 second. That's the goal. Okay, work in progress. But the most important slide is this one, which is I didn't do this work. This was done by a fantastic team of current graduate students and postdocs, as well as former group members, as well as theory collaborators. I collaborate a lot, in particular with Anne-Maria Ray's theory group, also Murray Holland's group, and for some work where we're, for instance, doing the superradiant laser work with Jun Yi down the hall. So with that, thank you, and I'm happy to take questions.
So I just wanted to, I guess, clarify or understand one part about the correspondence with the BCS Hamiltonian.
Yeah.
This corresponds to essentially BCS Hamiltonian in a 0-dimensional system or a quantum dot in the following sense that the consequence of the BCS Hamiltonian is superfluidity, where you can have supercurrent flowing in a particular direction and so on and so forth.
Yeah.
And that's sort of not captured, cannot be captured here because the Cooper pairs here have momentum 0 because you're always pairing C negative K and C minus K.
Yeah.
Is there a way to
we just to be clear, we don't know the answers to all these questions, which are great questions we were thinking about. But in a way I don't fully understand. Anna Maria has emailed me saying, I think we can see the equivalent of the Meissner effect. We can see other effects. So there are things that you can look for as analogies, but you're absolutely right. It's not clear to me, like, how far can we push this? I don't know. And so, like, in which ways can you make the correspondence, in which ways you can't? I think it's an open question. But there may be more connections than you think. Because when we were first thinking about this, I was like, you know, come on, like this thing I understand. And the more we talk, the more I go, well, actually, it's kind of the same. So. Mhm.
So my recollection is that this feature Hamiltonian was actually first written in the 60s in the context of superfluid model of nucleus, and then rediscovered in the context of superconducting nanograins by Thompson, and that is when they were studying smaller and smaller aluminum.
Sure.
grains. And eventually they went to the point where they could see very clearly where.
I'm sorry, I missed that part.
Very clear. If you have 25 electrons, 26 electrons, they would see a jump.
Mhm.
Because one electron is paired. So, well, this sort of motivated my first question. So, how many particles do we have in there?
About 1 million. Yeah, it's well within BCS mean field. What I will say is, and maybe I didn't emphasize it enough. You know, I put up this diagram of spectroscopic enhancement. This 18 dB, as far as I can tell, it's the most entangled stuff that's ever been generated in the universe. In other words, like, not only are you claiming there's entanglement, but it's not fluffy entanglement. It's like actual honest to God entanglement that you measure. So stop, you know, like, you can tell me about all this entanglement, but what can you actually measure? We actually measure it. So it's not ion traps, it's not Rydberg interactions, it's not, you know, superconducting circuits, it's that. So the reason I'm saying that is that we're really able to access in our cavity system way beyond mean field. So there is some hope that if we can understand how to control the mean field, and even at the mean field level, what goes wrong, maybe one day we can start accessing and looking for instance, beyond mean field effects in these systems. But that's a bit of a hope. I'm not saying that that's like, there's a clear path to it, but I'll pass that along. That's why I have some optimism. Yeah.
Possible to make interactions dependent, because if you make them random, it's very similar to sort of SYK models as you take that one channel where you know. So
yeah,
is there control of dependence?
Not great. I think if that's what you want to do, there are other systems that are perhaps better for that. But for instance, we can take advantage of the fact that you can make the coupling strength in some sense K dependent. So for instance, in a P plus IP, you get sort of a PQ term that sort of enters. And so for instance, we think we can do that and maybe even go to sort of models that would be related to higher partial wave, like D wave kind of superconductors. With the N-body interaction, we think that there are some exotic superconductors that rely not on 2-body interactions, but effectively like 3 and 4-body interactions. So we're curious, what are the connections between the kinds of interactions we can engineer now in those kinds of systems? We kind of are a little bit schizophrenic in the sense that we like to think about quantum sensing and what these things can do for quantum sensing, but then we also look and say, well, how is this connected to many body physics? Because we think actually they're intimately related to each other and they're going to talk to each other over time. And I think they're going to inform each other over time.
One more.
Can you quickly comment on like spectral gap versus BCS gap? Like you kind of emphasize that the like kind of leaking field is like you can also use that to measurement system. But does it imply that like the coherent system is also like kind of inadvertently being measured continuously, and how could that time scale compare to that?
It is. It just turns out that the amount of field that leaks out is so weak that on a given trial of the experiment, there's not a lot of quantum back action, that's happening on the system of interest. So we don't think that it's a highly perturbative measurement on the system, that leakage field. The spectral gap is really just trying to point out that there really is like there they were doing their best to figure out like, how can we get something to tell us about the interaction strength in the system? And so they came up with this idea of RF spectroscopy. It was Peter Zoller and someone whose name I'm forgetting, my apologies. You know, and so it was implemented by many groups, but, you know, they knew it was related to the BCS order parameter, but it was a little unclear exactly what the relationship was. And in our system, we can kind of clearly distinguish the two because we can sort of bias our system away from sort of equal populations in the system. And we can actually vary the number of atoms in the ground state and actually see that there's a difference between this. Again, we'll call it the spectral gap just because that's what was used in the literature because they didn't know what else to call it in this BCS order parameter. So there are actually different frequency scales that depend on exactly where the system is biased to.
Is it as simple to think that when you're changing the outputs in the ground state, you should just take the block vector?
Yeah, that's the beauty, right? Like, so, you know, when we change the number of atoms in the ground state, really is just like, well, we do like an epsilon pi and then a pi over 2 and then, you know, a 3 pi over 2. And then sort of look at as we deplete the ground state and we move away, sort of what this energy gap, how it scales. Yep. It's a funny spectroscopy because actually we don't have an RF field that we modulate. Instead, in some sense, what we do is we change the Rabi frequency of the coupling while holding sort of the system at a fixed coupling frequency. And by doing that, we can sort of see that, well, at a big enough Rabi frequency, you don't know you're off resonance and you just start coupling to this other state. So it's a weird way of doing it, but it turns out it's kind of equivalent on a basic physics level.
So let me encourage the students to go see him at the T. He's a very enthusiastic person to talk to.
Yeah.
At 4 p.m. in the usual spot.
Thank you.